continue bore you with a dynamic boring model. Not only statically boring, and now it's dynamically boring. Okay. Okay, so it's a dynamic labor force participation. Okay. And in this case, we go parametric and structure. Okay. Just to fix the idea. We begin with the static labor participation model we just talked about. Okay, now utility depends on consumption in age A, participation, and conditional sum of your characteristics. The same thing as before, leisure, cross leisure and consumption. And now we introduce this n. This little n here is number of kids. Number of young kids in the family, and we know that that could affect the leisure value. Okay. Yes. And also let C, little c, be the cost of childcare. If the woman works, think about it. If you don't stay home taking care of your kids, you have to take your kids to daycare. That cost. Okay. And Y is husband income. And then you have this budget constraint where your consumption is just husband income and the wage, the wife's wage minus if you participate, then you have to pay the childcare cost. Again, it's a very boring model. It's just a marginal cost that's constant. And we also impose a functional form on the wage. The log wage is, notice the difference here. It depends on S, that's the education level of the woman. S is schooling. And age minus h squared, and plus is psi, which is just a ID wage shock. Okay, you might want to write down some of these functional forms just to remind yourself what are the alphas, what are the gammas. Okay, give you 30 seconds to copy them down, and we might use them later. And by the way, I never post my lecture notes for graduate students beforehand because I always ask questions in class, and the question in one slide will be answered in the second slide. And what's the point of asking that question? And I try to play the same trick with my undergrad. With 100 students, 120 students in the labor class, and ask, well, would you guys prefer to have lecture notes beforehand or afterhand? And I always say the enormous advantage of having it after class, and then I would say, oh, let's have a vote. Who prefers to have it after class? And what? Nobody. So I always, what can you do? 120 students say before, yes, let's go before. And also, then a student asked me, a graduate student asked me, can you post lecture notes beforehand? I have about 6 students in my, or 8 or 9 in my class. I'm like, I already lost to 120 students in my undergrad class. I never lost this battle, ever. Okay, so you're ready? So, yes. And we also impose a functional distribution function for this wage, which is just normal. And how so state space? State space means the factors the information that you have when you make decisions at age A is just husband income, number of kids, schooling, age, and the wage shock. Okay, we assume that you observe your wage offer before you make the participation decision. And the state space observable to the researcher is without the shock. We observe the husband income, number of kids, schooling, and age, but not the wage shock. Basically, we don't observe the wage offer. Okay? So we can use the alternative specific utilities. If you participate, that's your income minus that's husband income plus your wage minus the child care cost. And if you don't participate, this is your utility. Okay? Then the decision rule as before. Now we have cutoff rule on the wage offer. If your wage offer is high enough, this is the cutoff of the wage offer shock, which is a function of the state space that is observable. Okay, so everything in the state space but the wage shock. Otherwise, you don't participate. That's a decision rule. So yes, that's exactly the same as what we said before. So let's imagine we have a cross section of married women, 5 of them, and we observe participation. And if you participate, now we don't live in the Mickey Mouse world. We don't observe your wage if you don't work. We only observe your wage when you work. Okay? And the husband income, the number of kids, schooling, and your age. Those are things we observe for every single woman in this data set. And the model parameters are these alphas. Alphas govern your utility. C, the cost of the kid, child care, and the gammas. Gammas are the wage function, and the epsilon psi, that's the wage shock dispersion. Okay. So we can form the likelihood again. The likelihood is just those women who participate, the probability of participation to the power that they participate, and the probability that they don't participate to the power that they don't participate. So this would give you the whole probability that you observe the participation decision for the whole sample. Oh, for those who participate, it also we have to have the probability that we observe that wage. Okay, that is also something that we observe. Okay. Okay, that's a likelihood function. And we can rewrite this for the participation women. Okay, the joint probability that we observe this woman works at that wage is just the probability that we observe that wage. And then the woman works, conditional on that wage. Okay, the joint distribution is just the marginal times the conditional. Now the first term is the probability of working conditional wage, which is, we know what it is, right? It's our decision rule. You participate if your wage is high enough. In this case, if your wage is bigger than this. Okay. Now, the first question. Oh, no, not the first question. We still have, yes. The first question. What values can this take? What values can this take? Even the parameters alpha 1, alpha 2, alpha 3, C, yeah, and given any y and n, what value can this take? The probability, yeah.
Greater than 0.
Great, greater than 0 because we know it's a probability.
Not 0.
What values can this take? It cannot be 2, it's a probability, right? So it's the true set is very small, it's just between 0 and 1. No. Literally this. I think this This is theta. What values can this take?
Easier to mistake 0 or 1.
Exactly.
Yeah, because you already have data, then you have to.
It's either 0 or 1. Why? Because the left hand side is a number. The right hand side, given your parameters, is also a number. 2 is either bigger than 1 or 1 is like 2 can never be smaller than 1, for example, right? So those are basically comparing two numbers. So this is degenerate. It's either 0 or 1.
But actually you already conditioned on the wage, so you already see the wage, right?
Yes, I see the wage. I'm just saying that.
It should be 1 then. I mean,
Why?
only people who get the wage is the people who participate in the market. Oh, okay, that's not.
That's the theory. Yes, I got you. That's the theory. But I'm literally asking, what is this? I'm literally asking a cat, is 3 bigger than 1? Right? So we can only have 0 or 1. So what's the consequence? Either the condition inside the probability statement holds or it doesn't hold. What would happen to the likelihood? Look at the likelihood. Okay, so this is the likelihood is basically this, right? And we take out one component of the likelihood, and it's this. And one component of this is either 0 or 1. And what happens to the likelihood?
This is easier to think too.
So the likelihood will not be degenerate. By degenerate, we mean 0. Only if there exists a set of parameters, alpha, gamma, c, and epsilon, sigma, such that this condition is never ever violated. If this is violated, as you said, then the likelihood is 0. That means for even just one household in a data set with gazillion households, as long as that condition is violated for that single household, the whole likelihood for the whole sample is 0, because the likelihood is just multiplied across household. As long as there is 1, 0, it's just 0. What does that mean? Likelihood is 0. What is the likelihood? How likely it is to observe this data according to your model? You know what? 0. You know what? This theory is wrong. Reject it immediately. So that's what we mean. What we mean by the likelihood is degenerate. Okay, no matter how many households you have, as long as there is one little household that violates this condition, the model is wrong. It's just never going to happen. Okay? So, that's bad.
Well, there's always measurement error.
Thanks for that. So therefore, in order for the likelihood to be non-zero, then the parameters must satisfy the set of restrictions that This thing holds for every single household.
Yeah.
And you know what? That kind of parameters is a zero probability event. You can't find such parameters. For example, it has to be satisfied for the person with the lowest observed wage for this case. And clearly observation will have this observation, even if it's, you can find some alphas that satisfy that person's condition here, that single person would have an extreme effect on the parameter values. Okay? So the likelihood will try to find the alpha such that this person is good. Okay? So that is bad. We don't want that in our estimation. We don't. So how can we avoid this? How can we avoid the degenerate likelihood? Great. So add some observables. That's what you mean, right? So add an additional error term to the decision model. For example, we can assume that alpha 1 differs across people. Okay, instead of a common alpha 1, we have an alpha 1 that is person specific. Alpha 1 plus the case shock. Okay? And if you do that, what complication would this give you? Let's work it out. Now, if you work out the algebra for the decision rule, you will find that whether or not you participate depends on this condition here. You remember we used to have this wage shock has to be bigger than certain threshold that you participate, right? And that's that you have an analytical solution. Okay? You know what that cutoff rule is exactly. And if you throw in, instead of alpha 1, you have alpha 1 plus epsilon I in the utility function, this would be the decision rule. Okay, you would participate if this whole thing on the left-hand side is bigger than 0. And you know what? You have the side here. You have an epsilon inside of the log. You lose the analytical solution. You don't have an analytical solution anymore. And when you don't have an analytical solution, I mean, it's not the end of the world, and people always do this. And when you don't have an analytical solution, you can solve the model by simulation. But simulation is costly, and as I promised you, I will go into that. I'm not going to talk about it. Sorry. So the point is, this is going to make your life miserable in terms of computation, but it is still doable. Okay. Okay, this is still doable, and this is a very reasonable way to introduce heterogeneity across households. And we believe, and households must differ from each other. Okay, so this is one way to do it. But we know it's costly. But it's doable, okay? And it's very sad. So there's always measurement error. Okay, for example, we can assume that observed wage or the reported wage is not the true wage. It's a true wage with some error. Okay, so this is your true wage, and this is your observed wage, and this is a measurement error. Okay, this eta is not in your model. The model is about this true wage, but it's just when the person record the wage, instead of 2.5, it was reported 2.8. Okay? So we assume that this wage is this measurement error is normal, 0, and with some standard deviations. And we also assume that they're not correlated with wage shock. Okay, so wage shock is a fundamental. It's something in a model, but this is just purely because of the typo.
What do you need log wage? Should we say in the previous slide you need to
Because of our means regression. We want wage to be positive, right? That's the way to do it. And we know that for a fact, if you regress log wage on education and age squared or experience squared, it's a very good way to capture the life cycle wage profile. That's all. Okay, so we assume it's not correlated with true wage shock.
So I could grab a little. So you motivated this as you write it down, we have this problem, like the function is 0, that's a bummer, we need to fix the problem. Here we get the problem, we can add measurement error. That solves the problem, I agree. I guess 2 concerns that I'd be curious to your thoughts about. Concern number 1 is, I guess aesthetically perhaps, I would like it better if we said, actually, this model is not very realistic. Now all models are not very realistic.
That's the first slide.
There's something important. Maybe in a particular substantive context, there may be particular kinds of realism that we want to add. Right? We want to make the model more complicated. Maybe we're concerned that there's very heterogeneous values. Household time, people are saying millers, why that's very reasonable.
Yes.
Maybe we're concerned that jobs are actually bundles of attributes, only one of which is the wage.
Yes.
And some of those attributes, like flexibility, may be very important to mothers.
Yes.
Yes. Or we can just say, measurement error.
Yes.
Ignore the literature on measurement error and wages because it's not normal like that, and go forward.
Yes. See, I carried out my promise. Even Jeffrey is bored.
I'm not bored.
No. So the whole thing, I agree that if I am going to estimate this, build up the model, I would introduce the other more realistic aspect into this model. For example, heterogeneity across household, as Jeffrey said, heterogeneity across jobs. People care about not only the wages. Okay, so those are the ways to do real things. But in order to illustrate how you can solve a participation model, let's go the baby steps. Okay, before we can run. Let's learn how to walk. Okay. So instead of this more correct. That's not the correct word. Way to do it. Let's do it this way. It's easier for us. Why it's easier? Let's take a look. The advantage is the decision rule is not changed because when people make their decisions, measurement error is not going to affect their decisions. Okay? So then you still have the cutoff value has an analytical solution, and the parametric restrictions we had before only holds with respect to the true wage, not with respect to the reported wage. In particular, your true wage has to be bigger than something in order for you to participate, but it doesn't mean that the reported wage has to be bigger than that thing. Okay, so that get us around that degenerate situation. So how does the likelihood function change? Right now, we have again, this joint participation and wage is going to be, first of all, you participate. That means your true wage shock is bigger than the cutoff, which is the fundamental in the model. Okay, and we also have this. This is the observed wage. And this is just a wage function, like the deterministic part of the wage function. And that's the error term. Now the error term is the sum of the true shock plus the wage shock. Okay, so that's the expression there. And given normality, this becomes this. Okay. Well, I send you the requirement for you to review the properties of two normally distributed variable and the sum of them, and you all did the homework, so you know how this comes. Okay. So this is just purely algebra, and you get this form here. And yeah, in particular, this standard deviation of the joint error term, that's the sum of the true shock plus the measurement error, is this. Oh, this is the type of this is the measurement error. And the rho is basically the fraction of the variance in the wage due to measurement error. Okay. So the component of the likelihood function for the non-workers, this is the component for the workers, right? It's participation times the density of the rate, or the density of the error term. Okay. And now the non-workers is just the probability that the person doesn't work. That means the CDF of the wage shock below the cutoff. Okay. Now, this model, although we have sort of a life in it, we have age in it, it's not dynamic. How can we make this dynamic? Well, how can we make this dynamic? Well, if you're fancy, I'm not that fancy. Adding saving, of course, it will make it dynamic.
Maybe number of children, choice of number of children.
Okay, you are all fancier than me. I'm just boring. In general, just allow history to matter, then you will make this more dynamic. Because when history matters, when you make decision today, you're for a forward-looking person. You will think about my decision today will affect my future choice or my future utility. Okay, you look forward. That's the dynamic. Okay, so that's how you introduce dynamics. And in a very boring way, let's just modify the wage function instead of ages. Remember, previously we had wage is a function of education and age. And age is not a choice. That's why it's not dynamic. Instead of age, let's make it experience. Okay? Specifically, assume that the wage a woman receives at age A depends on the number of periods the woman has worked prior to age A. That's the experience. And woman enters age A with K. So this is work experience in last period. The cumulative work experience in last period. And face which function this depends on education and your accumulated experience. Yes.
So if I wanted to be excessively theoretical, which
Mhm.
of course I always do, I would want to write down a dynamic programming problem.
Yep.
And have people forecasting future wage rates and all of this kind of stuff, right? And a lot of that stuff that would be in the dynamic programming, a lot of the stuff in the state variable would in fact be unobservable, like expectations about the future and so on and so forth. If I do something like that, can I end up with a policy function that's going to look like what you're describing? Or do should I just be happy to say, well, this is just an ad hoc way of introducing? I mean, ad hoc is not meant in this case to be a
Mhm.
because I think there's a lot of problems between
Mhm.
the But can I see this as should I see this as stepping away from the dynamic optimization paradigm? That's my question.
In that sense, I think it's very different from what you're saying here. Here, this is literally the interpretation here is almost like a technology.
Mm-hmm.
How your wage will evolve.
Mm-hmm.
It's a technology that the more you work, the more productive you are, then the higher your wages. It has nothing to do with, for example, perceived,
Mm-hmm.
and then from the perception, then you change people's behavior, and yeah, it's not going to take. Yeah. Again, another person gets bored.
I'm already bored.
Yes. And we assume conditional experience age doesn't matter. Okay. Well, you can throw in age. It's not going to add any complication here. And assume that wage offers are theoretically independent. This is a big assumption for a boring model we need it. That means the wage shock today has nothing to do with the wage shock tomorrow. You get a neutral, totally neutral from the same distribution. Or not the same distribution, totally neutral. Okay, so not necessarily the same. So the wage experience involves just add up your participation history. Okay, and we assume that at age 0, everybody has 0 experience. And given that wage offers depend on prior decisions, your prior work decisions, working at any age would affect your future wage offers. Because of this, a forward-looking household will take this effect into account when they make any decisions in any period. So we assume, and we always assume people are not crazy, they're forward-looking, okay? So now, we can augment the state space to include the current work experience. So now your state space is your age, your experience at the beginning of the period, husband income at this period, number of kids, education, and the true wage shock. For econometrician or for researchers, we don't observe the wage shock. That is equivalent of saying we don't observe the wage offer if you don't work. So denoting VA of this omega A is your state space, the maximum expected present discounted value of remaining lifetime utility at a given state space. Not only am I boring, I also introduced very long terminologies. Sorry. So literally it is just to maximize your utility, your lifetime utility. Lifetime means from, remaining lifetime means from today until the big A, that's the end of your decision age. And you add up your utility period by period. If you participate, your utility is U1. Don't, then it's U0. And you discount at delta rate. and you maximize this remaining utility by making a participation decision. Okay? And the value function, that is the expected present discounted value of lifetime utility, can be written as a maximum over two alternative specific value functions. Okay, it's the value function that you don't work, and the value function that you work. And each of the alternative specific value functions obey a Bellman equation. Who doesn't know Bellman equation? Great, everybody knows it.
Really?
That's also the pre-request I sent out. Okay. Well, but if you don't know, it's this. Okay. So, given your choice, okay, either participate or not, the value function, the remaining expected lifetime utility is your expected utility today, okay, conditional on your choice, plus the value function tomorrow, conditional on that you always make the optimal decision. Remember, V is the best between participation and non-participation. Okay, that's tomorrow, and it's also expected because there is shock, and it's discounted by delta. Okay, that's for any period smaller than the big A, when you still have a future. And in the last period, when you don't have future anymore, you don't have this term. You just you eat whatever, or you just maximize your current utility. Or expected your current utility. Okay, that's a Bellman equation. So given it's a finite horizon, we only have a big A period. The dynamic programming problem can be solved recursively from the last period. Okay, last period, second last period, third last period, until you hit the first period. You can solve it that way. And how do we solve it? Well, let's start from the last period. Oh, no. We have to complete the model. The model is incomplete yet. So take a look at what have you written down. Tell me what's not specified yet. We have already specified how the wage would evolve over time. And we have the utility function. Look, we have budget constraint. The number of children. The number of children. Where do they come from? Okay, so we need to make assumption about how children and also the husband income evolve over time. Children. First of all, so in empirical applications, when people talk about the wife's nature or wife's value of time at home depends on children. Basically, we mean young children. That means childcare. So let's say under age of 6. And to include that as a state variable in the model, we need to keep track of all birth within the 5 years preceding change. Right? That's how you get a kid of age below 6. You have to keep track of when they were born. Okay, that's one kid. And if a period is a year and births, let's say, can occur 1 year apart, then in order to update the number of children under age 6, you have to keep track of all the different ways to have had one child within a 5-year period. It could be 5 years ago, 4 years ago, 3 years ago, last year. And all the ways to have 2 children, 3, so on and so forth. It's almost like a combination problem, okay? And in addition, we have to specify the probability that a child is born at each age. Wow. That's not boring. That's not boring. Well, one possibility would be to assume that the probability of having a child is a function of your state variables in the model. We go very useful here, including, for example, the history of prior birth, the woman's age, etc. That's one possibility. Just specify the probability, but we know it's not right, because women might change their fertility when you change the environment. They might decide to have more kids or less kids, and if you just specify the probability, that's not the fundamental. That's not going to give you the real thing when you change the environment. Okay? So that's not good. Another possibility would be to model the birth of the child as another choice. Okay? Besides the participation, labor force participation decision, let's make the number of kids also endogenous. Let's make the household to decide on both. That's not boring. And because that's not boring, I'm not going to talk about it. Yeah, this is a way, like the real way you should do this. But as I said, let's take baby steps. And because children are so problematic and troublesome, not only because you have to buy iPads for them, but also because of all those problems. Let's avoid these issues by modeling the labor force participation of women after 6 years, after they have become infant, say from age 50 on. Those women do not have young kids anymore. Okay, let's focus on those women. That would get rid of the children. Okay, as a baby step, let's forget about the children. Okay, that's one part of the incomplete model that we just killed. All the children killed off. Okay, and husband income. That's what it is. Well, you can also model husband labor force participation, right? We can go fancy. We can go, they make a joint decision. They make joint decision of both couples' labor force participation decision. Whether or not you work or I work, we both work. We both stay at home. And we can go fancier by having a bargaining model. Okay? We can go fancier by having what's the name? Bargaining model, the other model. The efficient model. So we can go fancier. We can have the joint decision, but again, those are not boring. I'm not going to talk about them. And so let's go boring. Let's specify that husbands are just, in this model, husbands are literally just ATMs. They work all the time. And because they don't have a participation decision, it's only the income that we care about. Husbands are just like ATMs. The only use of husband is just get money from them. Okay, so the income would depend on the husband age. So age of the husband when the wife is of age A. And it's a function of the husband schooling and age squared. That's it. That's how the APM evolves. And we allow the epsilon A to be serially correlated, and it's normally distributed shock. You'll see. And what should we assume about whether this shock is in the information set at A? That means when the wife makes a decision to participate or not, we know that we already assume she knows the wage offer. And what about the income of the husband? Does she know exact income, i.e. the epsilon A here? What do we assume? There is not a right or wrong answer in this case. And we will assume it's not in the information set for computational reasons.
Excuse me? In what cases should we include this epsilon in the information set? I can't come up with an example. Could you provide it?
You mean why this is why this is realistic, or
why
this is not realistic?
In what circumstances will this assumption be not realistic?
When you make a decision whether or not to work, you might already know what your husband is earning exactly.
Yeah.
So, and also you can say the other case. You can say, well, when I make a decision, and I might know my husband on average will earn this, but I don't know what exactly his wage bill will be. That's this case. Okay, that's this case. So we were assuming it's not in the information set, not because it's more realistic, but it's easier. The answer is we're lazy. That's all. Okay, it's easier to compute. We will discuss the computational burden later. Okay, so given the epsilon is not in the information set, so what is the what's the expected husband income? Well, it's exactly this. It doesn't depend on the epsilon. And given the log normal distribution of the epsilon, this is the expectation of the epsilon. Okay? And that's the y bar. It's just a function, literally a deterministic function of age of the husband and of the education level of the husband, and a whole bunch of parameters. So we make the husband literally born. Okay. Now the model is complete. We can go back to the Bellman equations. Remember, the Bellman equation is this: when you still have a future, and when there's no future anymore, it's just the current utility expected. And why it's expected? The expectation is of future component is taken over the distribution of future wage shocks of the Y. Okay, why current one is also expected? Expected because, yeah, exactly, the husband wage shock is not observed yet. Okay, that's why this is also expected. So we have assumed that the future wage shock conditional on today's wage shock, experience, number of kids, schooling. Well, they don't matter. It's just independent of these things. Okay, and we assume it's normal. Again, in particularly this the non-serially correlated shocks is a strong assumption, but it makes the computation so much easier. Now, given that we are taking the initial decision period to be age 50, remember these are 50 years women when they enter the model. The husband age is just going to be, what is the husband age at age 50 plus the age difference, the age progress of the women, right? That means you don't have to keep track of this husband age period by period per se. All you need to keep track of is what's the age of the husband when the woman is 50. That's all. And also, of course, the woman's age, period by period. And again, we have the experience and the schooling level of the wife, and the schooling level of the husband, and also the wage shock of the wife. That's the state space for the household. But for researchers, again, we don't observe the wage offer if they are not working. Okay. So the value function at age A, that's the period when there's no leisure. Then your value function is literally the expected current utility. What is this? Well, it's just if you participate, okay? This is if you participate. It's literally you just eat what you have. That's the best way to go, right? There's no future. Just eat what you have. What do you have? You have the husband, expected husband income, plus your own income, your wage. Okay? The thing inside of the exponential is just a log wage function we just specified, right? And just take the exponential, get the wage. So that's the utility if you do work. And if you don't, then, well, this is what you have. You have the consumption, you have the leisure, and then you have the consumption times leisure, where leisure is 1. Okay, that's when you don't participate. Okay? This is so fantastic because we know how to solve the optimization problem right now. Okay, the value function, which is the best between these two, is just the best between this and this. And I want you to write this out. And the decision rule would be, look at this, compare this with this. Move this part to the left-hand side or move this part to the right-hand side. Just single out this thing. And again, you get a cutoff rule. You would participate in the last period if your last period with shock is high enough. It's just like the static model, right? It's so simple. Now, once you have this, and this is called the cutoff rule of the last period, given your state space. It's a function of your state space, but it's also age specific. Okay? Otherwise, you don't participate. And to solve the decision rule at the second last period, you need to calculate the expectation of the next period value function. Remember, this period, I care about this period expected utility plus my future value. And you have to give me my future value. And my future value depends on whether or not I participate today. Okay. So that means we need to know this. All this. Okay? The expected future value, where the expectation is taken over the wage job tomorrow for the Y. Okay? Now, we can take this expectation. See here? We have this. And I want you to take the expectation. Well, so what is the expectation? Remember, this thing is just the best or the better between participation and non-participation, right? So when is participation better? Participation is when participation is better. How often does it occur? It occurs whenever the wage shock is bigger enough, bigger than the cutoff rule. Where the cutoff rule, we know what it is. Is we have the function formula, we have the analytical solution already, right? And it happens with this probability. And if that happens, this would be your utility, right? Your income, your husband income plus your expected wage offer, conditional on that, conditional on the wage offer is big enough. Okay, this is a truncated distribution. Okay, anybody lost? Everybody on board? Okay, so, and then if this happens, when the wage is not attractive enough, you just stay at home, and this would be your utility. That gives you the expectation. And see here, we know everything. We know what it is, what this is, what this is, because we know what the cutoff is. We solved it in the last period already, right? You can do some manipulation here, think of some terms using the functional form to get the and using the fact that the wage shock is normally is log normal, you can get this thing. And it's just algebra is boring. Even I think it's boring, so it must be boring. Yeah.
When you say you solve the threshold of
Mm-hmm.
and well, actually you don't know the state space of the exact values of the data, the parameters. So what do you mean by you solve it and you can?
No. Here, are you talking about parameters or the state space?
Okay, I'm talking about the parameters. And
This is, the whole thing here is given a set of parameters. I'm just solving the model. Okay, given any alpha, gamma, I'm solving the x, the p, the participation. I'm not trying to change the parameters yet. I will.
So they are assumed known already.
Well, I'm doing all this theoretical thing where gamma is just a symbol.
Oh, okay.
Whether gamma is 1 or 2, I don't know yet.
Oh,
Okay, I carry all this gamma and alpha all the way through. Okay?
yeah.
So by that note, of course, this cutoff would have all this gamma and alpha through in it. Okay? And yeah, recall that this is a function of the state space that is observed by us, not including the wave shock. Like, just remind you what it is. Is this thing here? See? Okay. So it's something we know. Give me any K, S, and the husband which offer expectation, I can tell you what the cutoff is. And what the cutoff would be, it would be just a number if I also know the alpha and gamas, right? For each of the state space. And what does that mean for each of the state space points? That means I know this function. Give me any number. Give me any vector of state space here. I can pop out a number for this cutoff. That's what we mean by we know the cutoff function. Okay? It's one number for each possible value of the state space vector. Got it? So we know the function. Yeah, and so on and so forth. And then we can solve out the expectation of the value tomorrow, the last period, viewed at the second last period. Okay, it takes this form here. Okay, and what are they? It's just a function of the state space tomorrow. Okay, this is the famous Emax function. What's an Emax function? First of all, it's a max because I am choosing the max between participation and non-participation tomorrow. And it's an E expectation because I'm expecting tomorrow from today's point of view. So that's the E of the max. Okay? And having solved for the Emax function and the specific alternative specific value function for the previous period, i.e. the second last period would be this. Well, today's utility if you participate, plus the discounted value of tomorrow. Now, this is not something that we don't know. This is something that we know. Yeah, it's this. We know it. Okay? So it's not scary. It's nothing scary. We know it. And then we have the same for non-participation. Today's utility plus the discounted expected value for tomorrow, conditional on today you're not working. What's the consequence that today you're not working? That means tomorrow your experience will not increase by 1. What that gives you? That would give you a particular point in your state space. And as I said, given me any point in your state space, I can tell you what this value is. So that means I can tell you this is 3, for example. Right? It looks scary, but it's not. We already know it because we solved the last period already. Okay? Now, given this choice-specific thing, and we know that these things, this expected value tomorrow, just specific values of the Emacs function we have already solved. Okay, we already calculated actually. So once you have that, then you have the participation rule again for the second of period. You would participate if this holds. Okay. This whole thing holds. It's basically just comparing this whole thing with this. Okay, as you can see, the beauty here is this thing can be singled out analytically. That's the beauty. Okay, so again, you have a cutoff rule again, and that's the cutoff. And the cutoff, as you can see, this is the state space tomorrow, but it depends on today's space and the non-participation. That's how the state space evolves for tomorrow. So that means literally this cutoff rule is a function of today's state space. Now, otherwise you don't participate. You might feel lost a little bit because all these expressions look horrible and boring and long. But I guarantee you, if you, I will give the lecture notes. I think they will post it. And if you go back and just solve the algebra out of it, it's nothing. It just, in this lecture, all I want you to take out is the logic of solving things backwards. Okay.
I have a question about data. Data should be like that. If you work with other people, you don't work with the other people because they already fixed that. According to my life experience, it seems like only important is basically that when do they make decision that they will bigger markets.
Retirement.
Yes, in this adding model up to now, because the capital A, understand capital A as something like return A, actually taken as given. But we know that return
It's just stop working.
Yeah. You want to endogenize the big A, right?
The point that decision point is more important than the
Yes.
other decision point.
Yes.
In this framework, can you do that?
No, I'm assuming that A is exogenous. And exactly because of that reason, this is not a very good model. And exactly because what you're saying is not boring, I'm not talking about it. Remember, we're taking baby steps, but like seriously, retirement or stop working is a big topic, and there are like a lot of researchers doing research on this. And but in order to do that, you have to know this first. Even taking the exogenous retirement age, can you solve the model? Can you estimate this simple model? If you can, let's go fancier. Okay? Yeah. So you can continue doing this backwards and until you reach the first period in our model, which is age 50. And if we continue beyond that, then you have to be specific about the period, but we don't want to do that. So we stop at age 50. Yeah, so we have already solved all the participation rules of the cutoffs, which is now a function of the state space, and also the dynamics come from that the state space involves conditional on your choice.
It seems like up to now, you still assume that the life also is going to your market.
Yeah. Yeah, there are make sense, they're always there. So suppose we have longitudinal data on the sample of women, starting from age 50 to some final age, which might not be the terminal age A. For example, the terminal age A, let's put it 65. That's the time when you don't make any decision anymore. You're retired. But you might have a sample of women, some of them you might only observe up to age 60 or 58. But you can still estimate the model using their data. How do you do that? So we observe whether or not women works in each period, and the wage in period that she works, and all the state variables at age 50, the women's schooling, her husband's schooling, age, and the number of prior periods the woman has worked. Those are all the ingredients we need in the model, okay? And these are the initial conditions for the problem given the data we have available. So the likelihood contribution for household I is the probability that the sequence of participation decisions and wages of working periods over all the observed periods. From 50 to 58, if that's the 9 years are the total period that you can observe for that household. And as the static model, we need additional error term to avoid the degenerate likelihood. And again, we're throwing this cheap measurement error.
If we have very large cross-sectional data, so is it possible to use a cross-sectional data to estimate this model?
This model? Literally this model?
Yeah.
Yes.
Without the children?
Yes. Why?
Because you can see the distribution of the age can reflect to the time series distribution to some degree.
Then it is always dangerous when you try to use cross-section to approximate the time series. But it's not under this framework because there's no heterogeneity that we don't observe. Like households conditional on their observables, they're the same. Like there's no observed household permanent taste that we don't know. So in that case, we can estimate this model without time series, without a panel data. We can use cross-section. But that's because we're using a very boring model. Okay? Don't ever try to write a paper based on this. Okay? Don't ever. Okay? Don't even think about it.
Can I ask you a question?
Yeah.
So if we shouldn't write a paper based on a model like this, I mean, how do you feel about John Rust, right? How do you feel about doing a big whole very complicated thing?
Very complicated.
Well, doing the dynamic programming that takes you from birth to the end of life.
Yeah.
Yeah, so that's kind of.
But he has observed heterogeneity, right?
Yes, he does.
Yes.
Right.
That's a key here. That's a key here.
Yeah. I mean, the question is, what's key in moving away from this model? That's, I guess I'd like to hear 2 minutes on that, but only 2 minutes, because it might be boring.
The key from stepping away from a dynamic model, that's
Well, not stepping away from a dynamic model per se, but stepping away from this model.
this model.
Right. I mean, you've been very clear about saying that this is a toy model for purposes of teaching us things, right? But not a model that we should take the data.
No,
Right.
no.
So when we want to think about a model, say a minimal model that we might begin to take the data, what do you think are the key directions to move it? You could imagine, we talked about, you mentioned, different ways of introducing heterogeneity,
Yeah.
maybe more heterogeneity. You can imagine richer dynamics. This
Yes.
is my comment about John Rust.
Yes.
And my question is, which do you think is kind of good and which do you think is maybe less critical? Or are they all critical?
I mean,
Who knows?
it depends on what question you're after, right? If you really want to understand the dynamics of labor supply, for example, then I don't think, and if you're interested in the younger women's labor supply, and then I think it will be very critical to jointly model the fertility and labor supply decision. But when you do that, the problem is the model would not have a good time with the data, in the sense without any observed heterogeneity, permanent heterogeneity, in the sense that they're just some households, they're just permanently look different from others, conditional everything. So at that point, then it becomes critical to introduce this heterogeneity. This unobserved heterogeneity, on one hand, it is more realistic to have them in the model, just from a common belief. How can people be the same conditional observables, right? Or conditional unobservables? That's an argument, fine, but the key issue why we need this thing is from a more pragmatic point of view. Is just without them you can't fix the data. You just can't. You can throw in measurement error, but we know that's not good. It doesn't have any economics. I think that's perhaps my answer. So, yeah, we're running short of time. So then you can define the likelihood. Let's say the outcome in period A, IT, as the big O for outcome, would be just the participation at age A, time T, household I, and the observed wage. Okay, then for one household, the likelihood contribution of the household would be this series of outcomes, conditional on the state space at age 50. Okay, the parameters we have are the utility parameters, husband wage offer, wage income parameters, and the wage offer distribution parameters, and these shocks, including the measurement error and the discount factor. And even the assumption, okay, hold on here, right now. We have a bit here. The probability that how you reach the initial condition. Okay? In our case, the initial condition is the state space at age 50. Here's where the IID shock assumption kicks in one big reason. Even we assume that wage shocks are IID, for the purpose of estimation, we can treat the state space at age 50 as predetermined. That is to say, work experience at age 50, we can treat it as predetermined. Why? Because, for example, at age 49, when the wife is making a labor force participation decision, she is not using her wage today to predict what would be the wage shock tomorrow. If that happens, then you can't treat the work experience at age 50 as predetermined. But because of the IID assumption, we can. Okay? Because of that, then we can drop this bit off because it doesn't depend on anything. And then you have this likelihood function, the likelihood for household, and you have this for every household. And you can do this joint probability by conditional probability. And the conditional probabilities are just all those cutoff rules that are dynamic. Okay. So we have already seen that before. So this is important. How do you do estimation? How do you do estimation? I think he brought up this thing about, oh, what is the parameter? And how do you do estimation? First step, choose a set of parameters. Pick any set of parameters. Calculate the Emax functions for at all state points by solving the model backwards. That is, given alpha is 2, beta is 3, let's solve the model backwards. When you solve the model backwards, you will have the cutoffs for each state space point. Once you have that, then you can calculate the likelihood value for each person at that given, and also for the whole sample at that given parameter. Okay, that gives you a likelihood value for this given set of parameters. Then what do? You do another set of parameters. You do the whole thing again. You calculate the likelihood. This one, well, is better than the other one. Search again until you get the best one. See, that's where the computation comes from. For every single set of parameters, you have solved the model backwards. Again and again and again. That's why we're keeping the simple model very simple. We don't have any serial correlation. We don't have additional shocks. We have the husband income shock unobserved. So on and so forth. Those are because we're trying to save the computation for them. But nowadays, throw them in. The computers are very fast. Throw them in. Okay? And until you find the log maximize likelihood. Yes, quick.
I wonder, you mentioned such as Monte Carlo method to calculate the expectation?
No, that's the whole purpose of having this simple model. See, the model always have analytical solution. Don't need to use Monte Carlo, right? But if you have additional unobserved heterogeneity, for example, then you have to solve the model by Monte Carlo or simulation. Okay? So this simple model, you can literally know, given the parameter, you can literally use your hand to solve out the cutoff rule. That's the simple model. Advise you what it advises you. And then you can estimate the whole model. That's what estimation means for a structural model.
But
The dynamic structural model, yes.
But if we introduce error term to decision rules, we need to do Monte Carlo.
What do you mean by error term to decision rules?
I mean, add it to the.
You can add error term to the utility function, to the preferences, to the wage process. What do you mean by add an error term to the decision rule? The decision rule is derived from the utility function, the optimization problem. Like you mean, I know this is what I should do, but when I do it, I do it wrong. Doesn't make sense, right?
It doesn't really solve, it's also an accident.
But that's not a error term to the decision rule. That's an error term to the fundamentals in the model. Yes. Yes. Okay. Okay. So I don't have time to cover this, but fortunately, I already asked you to read it, and you all read it. You all read it. Okay. So they have a slightly more complicated model why their model is more complicated than the model I presented is because those additional features they introduced into their model are necessary for them to fit the data. Again, you see another trade-off. It's not necessarily true that the more complicated model is better. In a lot of cases, you have to modify your model. This is another thing you have to take away from this. Like this. You can throw in, this whole procedure, you can throw it in the computer and the computer will do it for you. But it doesn't mean that doing structural estimation means, well, I know this is the model. I have this set of data. Okay, there you go. Throw it in the computer. I stick there for a month, and then I will get the parameters. I'm done. Write up the paper, send it to JP. That's not how it works. That's not how it works. I guarantee you, you will fail. Because no model can explain the data without interacting between the data and the model. It's always, I have a model, that's my perceived basic framework. I try to use this model to explain the data, and I guarantee you, 100% sure, I guarantee you, you will fail. You will find that your model doesn't fit the data. What do? You modify the model. That's how you find all these additional features in their model. A lot of them are necessary to fit the data. And then you go back again, try and see how it works. But it doesn't mean that you, in order to fit the data, you throw in 1,000 parameters. That's not good. Conditional, you can explain the data. The more parsimonious model is preferred. Okay, so it's a piece of art. It's always model to data, data back to model, model again to data, until you have a harmony. Okay, this is a piece of art. I told you the boring things, but the piece of art has to be developed by yourself.